This is our last and final session of not only today, but of the whole conference. And our final speaker on this stage is Bartosz Milewski. Bartosz has a PhD in theoretical physics from University of Wrocław. After working as a postdoc at universities in Europe and States, he switched to programming and joined Microsoft. There he led the team that implemented the Windows search engine, and he has written a book about object-oriented programming in C++. His interest in parallel and concurrent programming led him to the study of functional programming and then to category theory. He teaches category theory not on his YouTube channel and has written a book, Category Theory for Programmers, based on his popular blog. When he's not working on all these topics, in his free time, he likes to do rock climbing. He's going to talk about why algebraic data types are important. Please give a big round of applause for Bartosz.
Well, thank you. This is really a great pleasure for me to be here for several reasons. One of the reasons is this is where I actually studied physics. This is the city where I studied, the university here. And then the second reason is that after I left physics and after working at Microsoft, I actually came back in the 90s, and as one of my students reminded me, I taught C++ here at the university. At the physics department, I actually started teaching C++ for a semester. So in a sense, I have my little contribution here to this fact that there are so many C++ programmers now in Wrocław, some of them my students. And back then in the 90s, C++ was not yet such a big thing, and an object-oriented programming in general was a relatively new thing. And I always try to look ahead, what will become the new thing, and eventually C++ became the big thing that it is, well, almost up to now, right? I mean, it's still popular, right? But this was in the past, and I always try to look into the future, and so I switched from C++. I started programming in Haskell, and then that led me to category theory and to math. So this is what I think the future is. Okay, so I'm sort of going to go against the general tenor of this conference, because I'll be criticizing C++ in a way. Okay, I think there are great things about C++, and there are things that are not so great, right? And we should look at other languages as well, and look at the theory behind programming languages, and we should also look at mathematics. And as you know, there are people who are talking about how important mathematics is in programming. We are all mathematicians, really. I mean, you might say, you might not realize that you're a mathematician being a programmer, but you are. We are doing mathematics in our own way. So looking into what mathematicians do that is related to programming is important, and it will become more and more important in the future. So that's my main point. But today I want to concentrate on types, on the type system. Okay, it turns out that the type system has very strong mathematical foundations, even though you might not notice this if you only know the type system of C++. But there are problems. Okay, so what is the problem? What's the problem with a type system? So without mentioning any particular language, most strongly typed languages have a pretty ad hoc type system. It's a type system that was built incrementally, and it was built bottom up, right? So like a lot of C++ programmers or C programmers, they would say, what's a type? Well, a type is like, it's how you store the stuff in memory, right? How the bytes are arranged, or bits and bytes, right? And that's a very low-level way of looking at things, right? As long as you are looking at things like integers, bytes, characters, and so on, well, that sort of makes sense, right? Or doubles. They are stored in memory, and there is a certain particular order of bytes and bits and so on. So, yeah. But then you are looking at data structures that are more complex. There are vectors, there are trees, there are linked lists, and there are data structures that won't even fit in memory. Okay, there are data structures like, even in C++ nowadays, you can start thinking about infinite data structures. Okay, maybe not yet, but I know that Eric Niebler is working on the range library, and his next big project in the range library is the lazy ranges. And the lazy range is something that can describe an infinite data structure. How does an infinite data structure work? It's not what's stored in memory anymore, okay? An infinite data structure will not fit in memory, right? So it has to be implemented lazily, meaning when you are accessing a particular thing using a particular offset in this data structure and so on, there is a function that's executed, right? And it either calculates this data or reads it from disk or from the internet and so on, right? So this connection between what's stored in memory and what a type is becomes less and less important. And then there is the problem of generics, and I'm using the word generics maybe not in exactly the same way as Sean was talking about, and he will probably be mad at me and say that this is not what Alex Stepanov calls generic types. But I'm thinking of generic types as generic algorithms, generic types as things that will work for multiple types, right? For things that don't look at the particular type, that are not specific to a particular type, like if you have whether you have a vector of integers or doubles and you want to sort it, it doesn't really matter whether it's integers or doubles, as long as you give me a way to compare them, right? And since I mean, if you listened to Sean's presentation, he went through the history of generics and how these things were added to C++. And they were added as an afterthought, okay? Oh, I mean, it was a great design and everything, right? But it wasn't in the language from the very beginning. So C++ has these layers of things, It's like it's like biological evolution, right? That you have some organs that used to do something else, and now they are used for something else, right? So this is how C++ evolved. I mean, like the templates were supposed to just, you know, if you want to have a list of integers of a list of booleans, right? You write a template. It's sort of like a better macro. But then they evolved into these beasts that are just now like totally a functional language of template metaprogramming and so on, right? Now, there is a good theory for types, okay? There is a mathematical theory. There are actually several mathematical theories, right? I mean, so Alex Stepanov has his own theory, which is more concerned about performance and how things are evaluated and so on. Then there is the mathematical theory of types. There's a type theory that's part of logic. But this is a very complex theory. It's like a very, very abstract. Even for mathematicians, this is like a very high level of abstraction. So no wonder this theory is pretty much ignored by most language designers. But the problem is that without these good basics, so like if you start building the type system from the bottom up and you just keep adding layers and layers as the need arises, you have to deal with things that happened in the design and they just don't fit as well. It's like if you design a system as one big thing based on some very solid theory, it should be much easier than if you just incrementally rediscover things. Is essentially the type system was rediscovered by programmers and all these elements, and I will talk about this, how the theory interacts with practice, right? And you'll see that these things that you know from programming, that actually they have mathematical basis, but it was discovered kind of later that they correspond to certain things. And for instance, the algebraic data types, right? The algebraic data types are really part of type theory, of this very, very abstract theory. But we got there from some totally different direction. And now that we are comparing this with what mathematicians are saying, we see that, okay, so maybe there is not such a great fit and we made a few mistakes there and we should have done it a little bit differently. So let me just like daze you a little bit with what a systematic type theory is. And you'll understand why people don't really want to learn it, because it's it's really so it's based on something called Martin Löf type theory. So there was this mathematician and he came up with this type theory, and it was part of mathematics. It was really, type theory was invented to fix the paradoxes of set theory. You know, there's this Russell's paradox and other paradoxes. Like set theory is paradoxical, unless you start doing some additional stuff. And one way of doing this is introduce types. Okay. So Martin Löf type theory introduced types that follow a certain algebra of types, and this is why it's called algebraic data types. And I'll introduce them one by one, so you'll see how they work. This is actually even more general, because it turns out that like the complete type theory, it contains also these dependent types, and you might know a little bit of dependent types from C++. amazingly, C++ in the templates, actually you can parameterize a template by using a value like an integer, right? Not only a template of class T, but it could be template int n, right? So this kind of dependence of type on an integer, on a value, is called dependent type. But what C++ is doing is sort of like just scratching the surface of dependent types. Then there is category theory, okay? And category theory, it turns out that whatever you do in type theory can be translated or modeled in category theory, and it also can be modeled in logic. So category theory is like Haskell programmers know these words, right? I mean, and more and more people actually start using these words. More and more programmers are talking about things like functors, not the misnomer, the C++ misnomer functor as a function object, right? But a functor is something that operates. It's a family of types with certain properties. There are things called monoids, and I heard monoids mentioned today, so I know that this is something people talk about even in C++ conferences. And of course monads, right? I don't know, were monads mentioned during this conference? I know in corridors there were, but yeah? Okay, cool. I mean, there was a talk about futures, right? And futures are definitely monads. Okay, and there is a third sort of leg of this type theories is intuitionistic logic, right? And intuitionistic logic is part of logic that is also called constructivist logic, where you actually look at theorems and propositions and proofs. So it's like operations on proofs. How do you make a proof of something from proofs of other things, right? And there is and all these three things actually are isomorphic. It's really the same theory, but it's using different language. So type theory, some subset of category theory, and intuitionistic logic, they are all the same. That's really a weird thing to say, but they are the same. They have exactly like one-to-one correspondence between statements. If you prove one thing in type theory, you can apply it to logic. If you prove it in logic, you can apply it to category theory, and so on. And the great advantage of having a well-defined type system that's defined using these algebraic data types and so on is that there is this wonderful thing called Hindley-Milner type inference, which lets the compiler figure out types of things. It's like, you know, strongly typed languages like C++, they have these very complex types sometimes, like the type of an iterator. You know, it's like people were writing these types of iterators for a long time, and they really got upset about that. And eventually, the auto keyword was introduced in C++, right? So auto keyword means that let the compiler figure out the type. There is enough information in my code, right? But auto only works in certain special circumstances. It's not totally general, right? But if you have a type theory, if you have the type system in your language that's based on type theory, then actually there is an algorithm that lets the compiler figure out the types. And why is it important? Because a lot of people complain, you know, I don't like writing these complex types. This is like a lot of typing, right? No pun intended. And you don't have to, really. I mean, in Haskell, we have this Hindley-Milner type system, and the compiler can figure out almost all types. I mean, there are some types that cannot figure out, but in 90% of the cases, it can figure out types. Doesn't mean that Haskell programmers don't write types, because types are useful in their own way. So they use types. But if it's obvious, you don't have to do it. The compiler will figure it out. So for me, generic programming is really about abstracting over types. So you want to write some code that is independent of the type of things that it's operating upon, right? So in order to abstract over types, just like we abstract over values, you know, it's like, what do? Well, we write functions that accept values and produce other values. We can do the same with types. We can write functions on types. These are called type constructors. Type constructors are function on types. And in C++, we have templates. Templates take types and produce types, right? So it is a function on types. Now, in order to define a function on types, okay, so how do you define functions in general? A function is defined, you know, here's a function, and on the right-hand side of the function definition is the implementation of the function. And the implementation, in the simplest case, is just an expression, right? What's an expression on types? Well, if you want to write an expression on types, you have to have some kind of algebra on types, so that you can say, okay, I take this type, and I add them, or multiply them, or take a power, or so on, okay? It turns out that you can do this. You can do operations on types, and you can form expressions on types, and you can use these expressions to produce functions on types, which is the way of abstracting stuff over types. And once you have this, well, then you can say, okay, so if I have function on types, can I now implement functions that take functions on types as arguments, or return functions on? So you treat functions on types as first order objects, right, that you can operate upon. And this leads, for instance, this is something that, well, in Haskell, for instance, people added this later when they realized that monads are useful, that you can have a type that accepts a function on types as an argument, or a type constructor. Okay, so it's like a higher order thing now. So there are these higher order generics like functors, monads, and so on. Now in C++, you don't really see, I guess, none of this, although it's theoretically possible, because a function on types is a template. A function that accepts a function on types would be a template that accepts a template parameter. So if you ever wondered why are there these template parameters, they are to do this kind of higher order programming on types. And now once you have these generic types, well, you want to perform operations on these at runtime, right? So you need functions that accept these generic things. And these functions that accept generic things, they have to work independently of what type you gave it, right? Therefore, they have to be polymorphic. So polymorphic comes up naturally when you have generic programming. You know, you have to have a function that takes a list of T, where T is any type, right? A function that takes a list of T and sorts it, for instance. That's a generic function. It's a polymorphic function because it accepts multiple types. Okay, and there are two types of polymorphism, and I guess C++ is mostly into ad hoc polymorphism, but there is this thing called parametric polymorphism when you can define a function that accepts any type, like any type that you can think of, it will work for it. There aren't that many functions like this because usually you want to do something, like you want to compare things or something, and not every type can be compared, not every type can be turned to string, except in Java, right? So a generic type has no properties and no operations, no methods on it, right? So usually you narrow down this kind of parametric polymorphism to some classes of objects. So let me talk about algebraic data types, okay? Because this is like the basic of type theory, and like anybody who does functional programming in Haskell sort of understands what algebraic data types are, but it's really worth spreading this information so that everybody knows what algebraic data types are and recognizes them. Okay, they exist in C++. So the first thing is products. So we'll be talking about products, sums, and exponentials. Okay, so this is the algebra. Product means you multiply things, sums you add things, and exponentials you take powers, right? So what are products of types? Products of types are implemented in every language, really. I mean, every language implements products. They are just given different names. So like the simplest product is a pair, because it takes, two different types and makes a pair from these types. So in C++, this is really a very complicated class in the standard library called pair, right? That takes two types, T1 and T2, right? And creates a structure out of them. That pairing of types is called a product. Why is it called a product? Well, because think of it when you have types that only have finite number of elements, like Boolean has only two, true and false, right? Color, let's say, has three, R, G, and B, right? If you multiply them together, you'll get 6 possibilities, right? It could be true with red, true with green, true with blue, false, and so on, right? So you get 6 possibilities. So a pair that contains a Boolean and a color has 6 possible values, which is 2 times 3, okay? And this is like a Cartesian product of these two sets. And this can be generalized to infinite sets as well. So you can have a pair of int and double and so on. You can also have, so this is a product of 2 types. You can have product of 3, 4, 5 types and so on. And usually when you have many types, you call these things tuples, right? Tuples of 3 types, 4 types, and so on. And if you have many of these, you probably want to give them names rather than say the first element, the second element, the third element of my tuple. So when you give them names, you call them structs or records, or you call them classes. Okay? So all these things are product types. And in set theory, so every type can be interpreted in set theory. This is not really very precise, but you can think of a type as a set of values. Okay, so if you think of a type as a set of values, then product type will correspond to the Cartesian product or a set of pairs. Now, in type theory, types are defined. So there are some fundamental types, and then you can produce new types by combining them. And these ways of producing new types are when you define a type in type theory, you do two things. You say how this type is introduced, the introduction, and how it's eliminated. What does it mean? Introduction means if you want to construct a pair of, let's say, int and bool, what do you have to give me? Okay? You have to give me a value of type bool, and you have to give me a value of type int. Both. And then I can create a pair. Okay? So introduction means really construction. So what does the constructor of a pair take? Well, it takes an element x of T1 and element y of type T2. And of course, in C++, this gets really, really complicated because you can pass these things by value, by reference, by move, by pointer. There are so many ways, right? But from the point of view of type theory, you just give it two things, and it produces a pair. And so in order to create a pair, you need two values. That's what type theory tells you. C++ tells you, well, you can create the type and then initialize it later, right? And usually this is not a very good idea. It leads to a lot of bugs. Okay? So strictly speaking, when you're creating a pair, you should provide these two values and initialize it immediately. Partial initialization is not a good idea. Elimination means the other side. So if somebody gives me a pair, okay, they say, here's a function, it accepts a pair. What can I do with this pair? Well, I can extract the first value, or I can extract the second value. That's all I can do with it, right? So this extraction, and this is like in C++, it's called get, and it's actually parameterized by an integer. So get 0 takes the first value, and get 1 takes the second value. They might be of different types, right? So this is, and so every type that you talk about in type theory has the introduction rules and the elimination rules, okay? And then there are some laws that say, well, if you introduce something with some value and then you eliminate this value, you should get the same value back, right? So there is some consistency that the stuff that you put in is the same stuff that you take out, which essentially means no mutation, okay? So type theory is really like a very functional thing to do. And if you want to do mutation, like in C++, then you get into a more complex system where you actually have to use monads. So almost all C++ programming is monadic. So you are using monads every day, okay, without knowing this. Okay, so this is the definition of get. It's really pretty complicated. Why am I showing you this? This is because this is sort of like upside down. These are like the simplest ways of combining types that are known in mathematics, and in Haskell, for instance, these formulas are extremely simple, basic. Okay, now in C++, all this seems like it's been added later as an afterthought, and it's really true, because without templates you cannot really have product types. So this is instead of building top down, C++ is built bottom up. And then when you get to this level where you say, okay, all these other languages, they have product types, and what do we do? Well, we'll use templates, and we'll use this kind of complicated expressions to implement simple things like product types. Okay. Now, so you see this. This is from the perspective of type theory, how you introduce and eliminate types. There is this other perspective from the point of view of logic. What does a pair correspond in logic? Turns out that a pair corresponds to conjunction, to AND, A and B. How does it work? Well, in this view of programming as logic, you say, if you provide me a value of type T, this is like a proof that T exists. Okay, so this is called propositions as types. So if you can provide a value of T, it means T is non-empty. From the point of view of logic, it means you have a proof of T. Okay? So in order to produce a pair, you need two elements, one of type T1 and one of type T2. Two values. So you have a proof that T1 is non-empty. You have a proof that T2 is non-empty. Then you can prove that T1 and T2 is non-empty. Right? This is how you prove the conjunction or logical conjunction. When is A and B true? When A is true and B is true. Right? So this is sort of like when you think about this as in logic, it's like, okay, but I have AND here and I have AND here. I'm proving AND using AND in my language and so on. But from the point of view of types, this is like simple. Okay, give me a value of T1 and give me a value of T2, then I can create a pair, and that corresponds to T1 and T2. Okay, so these are products. And as I said, products are everywhere in all languages, right? Sums, on the other hand, are sort of not so great. Okay, so what's a sum of two types? So a sum of two types in Haskell it's called either. If you take two types and you sum them. In general, these are tagged unions, and in a way, class hierarchies also correspond to sum types, because a sum. Okay, so let me show you how sum types are introduced. Okay, so tagged unions in C++ are implemented as variants, and this is also like a pretty recent addition to standard library, right? I mean, other programming languages had variants. I think Java had variants first, and then C++. I'm not sure, but so variants are sum types, and this is the definition of a variant the standard library. So it takes a bunch of types, right? So this is like a list of types, T1, T2, T3, blah, 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 right? And it produces a variant. In set theory, this is called a disjoint union. So it's a union of two sets. So it says, you have a set of integers and you have a set of booleans. A union of these two is just this. You have an element of a union is either an integer or a boolean, right? There's this either or. So how many different elements can you have? Well, of the union, you have the number of elements in the first plus the number of elements in the second, because you either have an element from here or an element from here. So you just sum them up, right? So if you have Boolean and color, you will have 5 possibilities. It's either true or false, being a Boolean, or it's red, green, or blue, if it's a color. 5 possibilities. Sum, okay? So this is sum type. And this is clearly seen in the introduction law, right? So how do you introduce a sum? Well, I guess you don't see that very clearly from in C++. But the idea is that you can construct a sum type by providing a value of any of these types. Okay, so like if you have a sum of integer and Boolean, then you either provide an integer or you provide a Boolean. So you see the difference between product types when you had to provide both of them. Here you provide one or the other. And it's a tagged union, so it's tagged by what you put in. So did you put the integer or did you put a Boolean? Now, there is a problem with this that sort of was missed in the type system. So from the point of view of type theory, this is called a disjoint union, which means that if these two sets overlap, so we were not talking about overlapping, like the Boolean and color are completely different from different sets, right? But what if these two sets overlap? And in particular, these two sets could be the same set. So in type theory, it's okay to have a union of integer with integer. It will just have a left integer and a right integer. So it's an integer with an additional tag. Am I left or am I right? Okay? This is something you can't do in C++ because they are tagged by types. So instead of position, right? It's like left, right. In Haskell, it's left constructor and right constructor. Here they are just tagged by the type. This is why there is only this one constructor, because it's tagged by the type. So if you call it with a Boolean, you'll get the Boolean, right? Now the elimination also, this is kind of an afterthought in C++. Normally the elimination is done by pattern matching, by saying, is it left or right? Okay? Was it constructed using the left constructor or the right constructor? If it was constructed using left constructor, okay, then it's of type T1. If it was constructed using the right constructor, it is of type T2. Therefore, if you want to write a function that takes a sum type, you have to write a case statement that says, is it left or is it right? And for each case, provide a function that will accept the particular type. So if it's a sum of Boolean and color, then if it's left, then apply a function to a Boolean, and if it's right, then you have a different function that takes an integer or a color or whatever, right? So this can be implemented as this visitor pattern in C++. It's done by visitor. So a visitor just knows how to deal with these different types and will figure out, okay, the union that you gave me has a Boolean, therefore I'm going to apply the function of a Boolean or this visitor of Boolean type, or if it's a color, then I'm applying a different function. Okay. But you see, this is like not really that familiar to C++ programmers. But product types and sum types are the very, very basic constructing blocks of types. Okay, so I don't know why sums are treated as badly as they are in C++. And again, this can be interpreted in logic. In logic, this is an alternative. Why is it an alternative? Because if you want to construct a sum type, you can either provide the value of A or the value of B. And the same is, if you want to prove an alternative, A or B, you either have to provide a proof of A or a proof of B, and it's enough. You don't have to prove both of them, right? That's what OR is. So sometimes correspond to OR. I want to stress this fact that these things kind of mesh together. It's like the type theory and logic are really the same. So that you see that there is a very, very strong mathematical foundation behind types. The next type constructor is exponentials. So powers, okay? So exponentials correspond to function types. And again, function types sort of entered C++ slowly. I mean, in C, function types didn't even have, originally, didn't have a good type. It's like the types of arguments, for instance, didn't have to be specified, and then they added more elaborate type system for functions and so on. Then of course there is the fact that the lambdas, which are a way of constructing values of type function types, were added very late in the game. Okay, so having first-class functions means that you have exponential types in your language. So in set theory, function types or exponentials correspond to, if you have two sets A and B, it corresponds to the set of functions from A and to B. Okay, the set of all possible functions from A to B. Now, so the symbol for this is in Haskell, it's A arrow B, functions from A to B. In C++, it would sort of be B of A. In mathematics, it's exponential, B to the power of A, where A is the argument, B is the type, return type. Okay. Why is it an exponential? Because if you think about it, how many different possibilities you have? Like if for finite sets, like, you know, let's say color to the power of Boolean. That's functions that take a Boolean and return a color. How many possible? It's B to the power of A, right? So so it takes a Boolean, so for every Boolean value, true or false, you will have 3 possibilities. So 3 times 3 times 3. Right? Did I say it right? Is that everybody checking my math here? Okay, so introduction. How do we introduce this type, function type? Well, the introduction is through lambda. Okay, so this is like the basic way of introducing a function. You just have some expression and you create a lambda. So this is something that's been added to C++, I don't know, in 2011 or something like that. And of course, there were functions before lambdas, right? But there was no way of introducing a function at runtime. It had to be introduced at compile time. Now we can introduce a function at runtime using a lambda. And the elimination of functions is very simple. Elimination of a function is just give me a value and I'll apply the function to this value. Okay, so this is how I eliminate a function. What can I do with a function? The only thing I can do with a function is call it, execute it, right? That's what I do with functions. And this is really the important thing. Logically, this type corresponds to implication. B follows from A, okay? You see why? Because in order to prove B, A has to be true, right? If B follows from A. So if you give me a proof of A, then you get a proof of B. Okay? So every time you implement a function, you are proving a theorem. Okay? Think about this. Because, an implementation of function says, well, if you provide me an argument, a value of the argument type, then I can prove the result. I just calculate the stuff and return the result, right? I have an algorithm here to calculate the result from the argument that you gave me. I mean, we're talking really functional programming here. Like, of course, in C++, you could get the stuff from global variables or something like that, or read from disk. But in functional programming, you only have at your disposal whatever you are getting as your input. Okay. Then there is this weird type, unit. Okay? And this is really, really confusing. Because unit, from the point of view of set theory, unit corresponds to a singleton set. A set that has only one value. Okay? So, but in C++, it's called void. Okay? This is like a major problem. Because, it's really hard to explain to people that void actually has a value. Right? This is because if void didn't have a value, then how would you be able to call the function that accepts void? Right? You have to provide a value. So, conceptually, you have to provide this value to a function that takes void in order to get the result. It just, otherwise it wouldn't make sense, wouldn't be consistent with everything else I told you, right? So there has to be something like this. But, it's a function that returns a void, right? What does it mean? Well, it produces, if void had no values, then you would be producing a value of an empty set. Empty set has no values in it, right? So it's really impossible. So in set theory, this is a singleton set. The introduction of unit, so now I had to switch to Haskell notation because C++ doesn't have the concept of unit. So the introduction is you can get a value of unit from nothing. It just is available in the atmosphere, sort of, you know. It just is. It's like if you tell me, well, give me a value of Boolean, well then, do you want true or do you want false? I don't know which one do you want. But if you say give me a value of unit, well then there is only one choice. Here it is. Okay? There is no elimination because unit contains no information. It just is. Okay? Therefore, from the point of view of logic, this is just the truth value, the truth. Okay? You can prove truth from nothing. You know, it's like truth is true by definition, right? And there's only one possibility. Okay? So, this is an exercise. What is false? Right? Okay. Now, once you have unit, you can actually start constructing more complex data types. For instance, Boolean, that I talked about so many times, you know. Boolean is just a sum of two units. Can you see that? It's like, because a sum says it's either left or right, and what's the value of left? It's unit. Well, so it has no information. The only information in a sum of unit plus unit is whether it's left or right. And then you can call left true and right false, or other way around if you want, right? So this is really a sum of two units. And unit has only one possible value, so a sum of two ones is 2, right? So Boolean is just a 2. So you see the nice algebra there? Now there are more of these algebraic identities. Okay? So for instance, and I'll be switching now to more of a Haskell notation, but I think it will be kind of obvious what I mean. So this is this identity. 1 times A equals A. Okay, what does it mean? 1 is unit, times means product type, so a pair. A pair of unit and A is the same as A. Doesn't contain any more information than A itself. Okay? Now in C++ we would probably want to write something like this. Pair of void and A is A. But this is bad C++. C++ will not accept it because C++ treats void as a very, very special bad thing, right? It's like every time you write a template, you have to say about what if the type is void. There's a special case and so on. But void is not really a special case. It's just this one type called unit, okay? And it has only one possible value. So if you pair a unit with some A, there's no more information than A itself. And you can show it by showing that given an A, you can always produce a pair void A, right? Given a pair void A, you can always extract A out of it. So A and pair void A are totally equivalent. Okay, here's a more interesting example, right? Now we are using exponentials. So if you follow, an exponential is a function. The exponent is the argument type. So a to the power of b plus c, it means these are functions from a sum type, b plus c, to a. They take a sum type and return an a. And they should be equivalent to a pair of functions. One takes b and returns a, and the other takes c and returns a. Okay? So here it is in Haskell notation, because this is much simpler. What it means that if you have a function that accepts a sum type, then you have to do case analysis and figure out, is it left or is it right? Okay? If it's left, then I have to apply a function that takes b. If it's right, then I have to apply a function that takes c. So I need two functions to implement a function from a sum type to a, right? I need one function that takes a b and one function that takes a c, right? Okay. And then here's a simpler case, right? So a square is equal a times a, right? Very simple algebraic identity. Square, well, 2 means 1 plus 1, right? 1 plus 1 is Boolean. So it's a function from Boolean to a, and it's equivalent to a pair of a's, right? A times a, that means pair of a's. Okay. Well, yeah, because a function from a Boolean to a contains only two values, the one for false and the one for true, right? So you can memorize it as just two values. You don't have to calculate anything. So that's the notation. So function from bool to a is the same as pair of a's. And this one is very interesting. I don't know if everybody can see it from the back. A to the product of b times c is the same as a to the c to the b, right? Which means that if I have a function that takes a pair bc, or in other words, it's a function that takes two arguments, b and c, and returns an a. Okay? A function of two arguments is equivalent to a function from b that returns a function from c to a. Okay? This in functional programming is called currying, and this is some. I think in C++ we call it bind, right? Like you provide one argument and you get a function of the second argument, right? That's called currying in functional programming. And it's a very important property of the exponential. Okay. And of course I have a lot more stuff I could talk about, but my time is running out. Okay, so maybe I'll conclude this. Okay, I'll show you. You know, it's like I have a bunch of other stuff here. Oh, I can't really go fast from in this, huh? Infinity and beyond. Yeah, you see, lots of stuff. So I just want to show you that you can go with this algebraic stuff over and over, you know, and it's like, and you get to things like existential types, for instance, that nobody even uses in even in functional programming. People don't know much about existential types, you know. It's like, but this is very, very important part of type system. There is recursion, okay. Then you can do things like solving equations. Okay, it's like a list is defined using this equation in which you have an infinite sum of products. Okay, this is a cool one. So Right? So let me show you this. So you have an equation, list of A. LA is like a function of A, okay? It's a list of A's. List of A's is 1 plus A times list of A. So interpreting this from the point of view of type theory, this says that list of A is defined as it's either an empty list. An empty list is a unit, right? It has only one value, one possible value, empty list, okay? Am I an empty list or non-empty list? So it's a sum, empty, non-empty. So it's a unit plus, and what's a non-empty list? A non-empty list is a product. It's a pair, right? Which has the head of the list, which is of type A, and the tail of the list, which is of the type LA. So it's a recursive definition, right? So it's either empty or it's a head with a tail. Okay? That's the definition of a list. And then you take this equation and you just solve it, okay? So all these steps here are really bad because you cannot subtract types and you cannot divide by types, okay? You can do this algebra, but the final result is that, okay, this is 1 over 1 minus A, and that's just like, that's a sum of an infinite series, right? A to the power of n, right? Geometric series. That's, I don't know if everybody remembers the formula from school, right? So if you write it down now again, so LA is equal, so the sum, infinite sum, it starts with n equals 0, so it's 0th power of A, which is a unit. So it's unit plus A squared plus A cubed plus so on, so on, so on, right? And it means like a list of A's is either empty, or it contains one value, or it's a list of 2 elements of type A, or a list of 3 elements of type A, or 4 elements, 5 elements, and so on, okay? So this is like a non-recursive expansion, but it's an infinite expansion because the list is either empty or 1 element or 2 elements or 3 elements and so on. So it's an infinite sum of tuples, bigger and bigger tuples, okay? So that was the fun example. So this is my definition of generic programming, and then probably I will be beaten over the head about this. But for me, generic programming is just programming with types, right? And you have to have things like functions on types, which in C++ are templates, really, right? But you build these functions on types using arithmetic expressions, and so you have algebraic expressions. So this is where this algebra makes sense. You know, it's like you have to define functions using some kind of expressions, and these expressions are formed using algebraic data types. And then you have recursive data types, which are solutions of these algebraic expressions. Okay? So that's it. Thank you.